So today we'll talk about a big graph analytical engine. Actually, this is more like a report of a current work because it's still ongoing. Actually, we just started recently. So I will just introduce some background and then talk about its current status. Firstly, actually, I know many of you has know me and talked to me in the previous TUC meetings, but somehow I have to make an introduction again because there's something changes not everyone is aware of. So previously, I have been working with IBM T.J. Watson Research Center for more than 5 years, and I was in New York. But I made a decision this year, and I separated from IBM T.J. Watson Research Center, and I joined Huawei Research America in California. So in this April, I take a plane and relocated to the Bay Area, just 20 minutes drive away from this place. Huawei, I think probably many of you have heard about this name, but here I want to give a little bit more detailed information about this company. Traditionally speaking, this company is a telecommunication company, so it produces like telecommunication encrypts and some network devices. And it's a very big name in that area. But recent years, this company has made a lot of changes and they want to expand its business, especially in the IT market. So currently, the company is organized in this way. It has like 4 big parts for business, especially for the consumer BG. BG stands for business group, and the consumer BG basically is in charge of cell phones, laptops, something like that. And the enterprise BG is taking care of the cloud infrastructures, big data analytics, and all kinds of services that we want to provide to the big enterprises. The carrier BG is a traditional department which is maintains the market on the telecommunication area. It's pretty big. Then product and solutions, the other departments in charge of all kinds of other stuffs. Then, besides of the big business groups, we have a couple of other organizations or divisions in the company. One of them is called the 2012 Laboratories. This is one I'm actually working with. Why it's called this? This name is a little bit weird, and someone may think because this name was created in 2012. Well, actually, what I heard after joining companies, it's not the truth. It's named as 2012 because of the movie. Probably we know about it. A couple of years ago, there was a movie about it says the 2012 is the end of the earth, but someone built a Noah Ark to save the world. So this is the meaning, or probably is the task this lab should deliver according to the high-level managers. So this lab is supposed to deliver the new technologies, not just within the current business area, but also in other business areas as well. So if there's some significant change on the market, for example, in the traditional telecommunication area, then how this company can survive. So this is what this lab is doing. Currently, this company has, if I'm correct, has more than 170K employees in all over the world, and it has most of its incomes right now from the maybe out of China. I would say from many countries. So but the headquarters of this company is in Shenzhen, in the South China, and its research institute is kind of all over the world. Currently in Santa Clara, which is very close to this area, is the headquarters for research in America. Then they have some research centers in Russia for mathematics, and in France, and somewhere in Germany, if I'm correct. Okay, on this page, I show some numbers about this company. Basically, it includes the revenue, some profits, and some other numbers. Well, the currency usually CNY stands for China yuan, and basically, I think $1 is about six China yuan. So actually, revenue is quite big. I was comparing it against with my previous employer. IBM is about half of it. Then the growth is very significant, as you can see. On the first chart, show the growth like it's more. Even the very traditional departments growth and more than 20% a year to year in comparison, and the department I think my business is more close to is like enterprise business. It's about like 40% growth last year, and then if you're looking at the geography distribution, then China is take about like 40% of the income, and growth is about 50%. But Americas, Asia Pacific, and other parts of the world takes the major part of its income. So this company is kind of going to the IT department, but of course we don't have the accumulation of some technologies over the past maybe decades or so. So this company right now is very open, and we collaborate with the universities, industry partners like startups and other companies, and also we participate a lot in the organizations like some standardization organizations and some other non-profit organizations. So we try to accumulate more talents and go to those markets as soon as possible. So. Okay, let's go to some more details about what we are doing. So right now I'm in the American Research Center and working on the big data analytics and the management. So this is like a team here. So currently we are concerned about some technologies like NLP, graph, then traditional machine learning, and some deep learning. So in my team, we basically work on the graph technologies to power the big data analytics platform. And in terms of the application, we're concerned about some traditional financial area, which we assume is one of the market segment who want to embrace the big data very soon. Then the consumer area, like the cell phone, because the market is pretty large and they provide natural data for us to do the analysis, as we can see from the early talks today. Then the very traditional telecommunication area, and also the cloud. The cloud is a big business right now. Next, I want to say even in the very traditional areas, they bring a lot of new stuff out nowadays, and our technology, regarding LDBC, is very useful here. For example, in the traditional telecommunication area, they want to make a lot of changes to the traditional network. It's just similar to we have a cloud. On the cloud we have virtual machines. On the networks they want to have some virtual networks, and therefore they for all kinds of hardware vendors, they should support some standards like OpenFlow. Then on top of it, we can build a unified control plane for all the networks in the world, and this is called software-defined network. You probably heard about this term for many times. And on top of this software-defined network, we could provide some unified operating systems, just like we have operating system on the laptop, on the servers. And ONOS is one of the open-sourced operating system for networks. So if we look at the recent architecture of ONOS, actually it's very interesting. They have a graph database on top of it. Actually, this is very straightforward, right? Because if you think about the very fundamental element in a network, like switches, basically it's like a vertex in a graph, right? And the linkages are like dynamic edges in a graph. So it makes pretty sense to have a graph database, or at least a graph layer, to represent the current status of the network. Then we could do all kinds of analysis on top of it, and we could feed back those analysis to the data plane to control those switches in a more smart way. Right. Traditionally, I think we only compute probably some shorter paths, some optimized paths. very simple graph technologies. But right now, we could see, how important some vertex is, and how we could like partition certain networks to avoid possible, outage of service. So this is one of example we want to see why we want to explore the graph technologies on top of it, and this application is very specific. So regarding technology, let me give one more specific example. Eventually, for the network, it's like an infrastructure where we want to propagate information, right? So the information is like walking throughout the graph, and the graph you can view it as a network right now. So what is the impact of topology of the graph towards the information propagation? This is of course a typical graph analytic problem. Like what we do some simulations here. Like the x-axis here represent the time tickets. Okay, and each time tickets we will modify the graph structure a little bit. Then the information propagation will be impacted because of changes. And we could take different policies to control the network modification. Then, of course, the information propagation will be at different rate, and some propagation can even be stopped. So so the y-axis that shows the influence. So as we can see, if we really want to help some information propagate as soon as possible or throughout the whole network, especially some important notice, right? We want to send out. Then we probably want to take policy that as soon as in the red curve. Then the information will be reached. We'll reach out to many vertices in a very timely manner. However, if we find some information actually is kind of like a virus or it's a rumor, then we want to stop it. So we could take another policy here to modify the connection between those switches. Then those information propagation will be stopped very quickly. So this is a very specific example how the graph technology can help in the traditional telecommunication area. Well, there are more applications, especially when we look at the enterprise market. This graph actually is a graph. It's a financial graph. We use this graph to show the different transactions among the accounts. Each vertex here, you can view it as an account in a bank or insurance company. Then the edge represents the money transactions across different accounts. We aggregate those transactions over a time area and give such a graph, and we visualize it and show the wealth represents the amount of money. If we perform certain like a circle detection on this graph, then we may find some potential money launderings. By money launderings, it's like we transform this money out from a small group in the network. It goes through all kinds of other vertices, then it goes back. So in terms of the data transfer, what is the graph traversal patterns is like circles. Then some for in the social security areas, I think Palantir did a very good job, and previously SystemG also did some similar job there. So this is also area. Then we also concerned about to extend the graph to a larger area to incorporate with other technologies. For example, we combined with time series technologies to analyze, the data changes over time, then to provide, more data. And this data actually typically cannot query directly from the raw data. In some, forums or papers, they call it like a blank data. It means that the big data is big, but they just provide the obvious information to us. If we analyze their interconnections, actually we could find more information, and it is dark. It's called dark information. Then if we combine the network against some statistical models, then we got like Bayesian network, a very powerful, inference tools. It's not something new, but when we go to a large scale, the technical challenge on this area is still very, very strong. Then hypergraph, when we want to analyze the relationship among multiple entities, typically is a joint relationship among them, because if we look at them separately, the effects actually is different. Then we leave this kind of graph. And this graph is mathematically is a natural extension of the current graph. But if we want to use the current graph, database or data processing systems to do the computation, actually is really not convenient. And the hypergraph actually has a natural relationship to the Bayesian network here, because they all can be represented and solved by some tensor analysis. Then traditional data knowledge graph is, I think this has been addressed in many talks, so I will just skip it. But the challenges here, we don't need to go through it one by one, because I think we more or less know that the graph is probably one of the most challenging problems big data analysis, especially, when we're talking about its data locality and I/O or disk I/O performance. But anyway, we are building such a platform on heterogeneous infrastructures to support large-scale graph analysis. Here it's not just the graph structure analysis. It actually involved a lot of properties, and so I think it's basically under another dimension, because many technologies that we need for managing the properties are kind of similar to traditional data management. Okay, so we divide the whole system into 5 layers. The infrastructure, then the data management basically is like the graph databases. Then there's multiple graph engines, because we know the data access patterns and some computational behaviors of different graph algorithms are so different. So it's really hard, or probably technically impossible, to use a single engine to support all the computations and deliver high performance. We don't think it's possible. So we kind of work with different engines, but all the engines are built on top of the same data management layer. Therefore, the information can be easily interchanged. Then on top of graph engines, we build the graph analytics, and for different engines, they support different analytics, so that we can achieve the better performance. Then on top of it, there's a large-scale graph visualization. This is pretty I think I wouldn't say it's pretty straightforward, but it's kind of like a standard technology. So if we look at the architecture of a system, then we can use a graph like this to show it. It's a little bit, as you can see, it's a complicated system, because for each part, we have to use different technologies and put them together. And one of the challenges here is that if we rely on building open source technology packages, solutions, the integration actually can bring a lot of overheads in practice. So then it also brings a lot of challenges to us. And so on this part, we also want to, collaborate with universities and some other companies to explore some, efficient solution. Right now we focus on the graph engine side, the regular graph engine side, and we achieve some. It's still ongoing, but currently I think the preliminary experiment looks quite good for us, and. But considering we have to support the more complicated graph models, because graph models combined with time series analysis, and graph models combined with the statistical models, then we still need more bandwidth or more resources to solve this problem. So one thing that we used in the in the regular large-scale graph support stack, we were looking at some existing solutions for graph, and we know the performance challenges for graph computing basically comes from the I/O, like data locality, and eventually it was caused by the randomness in data access. It's a pretty common data access patterns in graph computing, and the graph tree is it's something have been here for many years, and the way they organize the data is kind of like they want to reduce the randomness. Of course, in their papers they want to emphasize one side of it, and they use a PageRank to do experiment to show good performance, because in PageRank basically you don't really need to follow the topology of the graph to do the traversal. But anyway, it provides a uniform way you can access the data, and you can reduce the randomness. But of course, it's not enough. But somehow, if we just look at the way how they use parallel sliding window to access data, we can actually map it back to a just matrix representation. Then we could see this pattern actually is quite straightforward, right? It's not as fancy as it described in the paper, but if you map it back to the matrix, it's quite straightforward. It's just like traditional blocked matrix data access. So the simple pattern here actually can help to some extent, because the pattern is simple, so we know what the pattern will be in the next step, and therefore we could prefetch data according to such patterns. Then by prefetch data, we could possibly hide the overhead from the I/O, disk I/O, or network I/O. So this is a starting point which inspire us for the design of our current system. And of course, you probably don't want to use this technology directly unless you just want to use a single machine, because it's easy to tell by looking at these blocks of the sparse matrix. The blocks kind of can be quite sparse, and sometimes you have to access multiple blocks to get a few data for particular vertices. So as a result, you want probably combine certain blocks together to make it a little bit dense. It's okay. Actually, it's okay. You access the data in the block mode, because the machine, the computers always access data in that mode. But the issue is that you want to kind of balance the workload across different blocks here. And in the meanwhile, you don't want to lose this simplicity by the graph tree inspired us. So what we can do is, we still partition a block, but when we partition a block, we give some blocks may have multiple IDs. So according to the graph tree, we could access the data in this way. We can organize all the edge set as a flow in this way to feed into the memory and eventually feed into the CPUs. However, because we kind of partition, we kind of reorganize those edge blocks, edge sets. Then some of the blocks, the blocks in the middle, may have multiple IDs. So as a result, some of the blocks here in this flow actually are physically the same block, which actually turns out increase the temporal data locality. Especially in this part, actually, once 5 is brought into memory, basically you don't need to bring 4 and 5 and 6 again. It's physically the same data set, has all the information we need. So this is a way we could kind of organize these blocks, or we could leverage the simple data access patterns and preface the data and organize those data into a flow, and then we feed it into the computation units. And by this way, we try to hide the overhead from the I/Os and make the overall system, the overall throughput better. So this system, we just start building this system recently, so we don't have many details or many data to report. But I asked my colleagues to do some experiment. This week I think maybe it's better we show some numbers to the audience. So we did some experiment, and the preliminary experiment looks good. So on the x-axis we have a graph of different sizes. Then we use graph G as the baseline to compare with, and we have two different modes. One is all shard, one is one shard. But when we use all shard, I think it's kind of like a default mode for graph G. And when we use one shard, it's more like we want to bring everything to memory to do the computation for graph G. And then HC flow is what we are using right now. So on this chart, actually, what we show is the pre-processing. The pre-processing for graph is basically to generate the shard, and for us, it's like we just generate the physical blocks and assign different block IDs to those blocks, and some blocks may receive multiple IDs. And according to those IDs and data patterns, we will have kind of like a scheduler to prefetch the data. And on this chart, I think it shows the running time. And here we exclude all the time for the I/O access. So here is basically the pure computational time, and as you can see, the speed up is very, very significant for compared to the baseline. And no matter which mode you are using for baseline, even we compare with the pure in-memory computation, is still much faster. There are more details than I can include in the chart, including some data parallelisms we used. Which explains why we could receive such significant speed up. And then, if we consider both the I/O access and even the pre-processing, then we consider all the end-to-end execution time. We still consider there's good speed up on top of it. Of course, right now we only get some chance to do the experiment and some synthetic data and a very preliminary step. But I think it looks promising, and we will hopefully next meeting we will provide a lot of details, and we will see the behaviors and the speed up in a more close in more details. So that is what I want to address, basically what I want to address about our system. But as I say, it's still new. We are still building it, and we are looking for partners and collaborators to help, because it's a big platform, and it involves the multiple disciplinary knowledges. So this is a brief conclusion of my talk. So, and yeah, I think basically it's my current work, and Huawei we just started in probably 2 months. So hopefully next time we will have more details than I can to present to you guys. Okay, any question?
I'm just curious, in your graph visualizer, you have separate, how does it visualize it? Large scale visualize?
That's basically, because of the different applications, or what kind of properties you want, what kind of information you want to see from the graph. If you want get some overall information of the graph, basically it's impossible for any current the graph visualization tools to visualize a very big graph. So basically, what we do is that we offload the computation to the data processing side. We do the sampling of the data in our kind of a graph processing layer. Then we provide the result to visualization, so then they can use their a browser to finish the work in a kind of near real time. Yeah, I think. one of the issues is that for the traditional visualization, they just want to show all the vertices in your graph, and they try to find a better layout so that the result will make better sense. But the pixel on the screen is always limited. Actually, it's much less than the number of vertices we have in a big graph. That's why if we just use the traditional visualization tool, it doesn't work. So we have to produce different tools. If we like in the example, we have a visualizer to show that part. But if you want to look at some details, like in a hierarchical way, then we provide different one. Yeah, it would be great if we could eventually join them together. Yeah.
Any more questions?
So in order to make these charts, right?
Yeah.
You need to first get this data access patterns, and I believe we're dependent on the application that you run, right? So to measure this data access patterns, do you need to run this application first on the same graph? How it's been done?
Right. So it's correct that data access patterns are typically associated with the specific applications. So what we observe that if we look at the overall patterns, for example, for many graph algorithms, actually what they do is that they grab the information from its neighbors, they process information, and they send out the new information. This is basically what the guess model is doing, right? So many algorithms actually they could be expressed using such a guess model. Under the same model, then we have basically pretty same data access patterns. So this pattern is probably not the best one for a very specific algorithm, but it's a durable one. It's a one that we can unify. Different algorithms. So then I think as a platform, we provide such a support so that we could support more algorithms without do a lot of dirt job one by one. Yeah.
Any other questions? Okay. Thank you, Yinglong.
Thank you.